Hi everyone, in this meeting we're going to talk about prime numbers and prime factorization. We're going to find the prime numbers and then use them to determine if a number can be prime factorized. So why do we need to prime factorize? Prime factorization is very important in RSA because we need to use it to find P and Q. By finding P and Q, we can find phi n and then find D, which helps us to crack the message. Because in RSA, if we're an outsider, the only piece of information that we don't know is the value of D. So by prime factorizing n, we can find phi n and then find D, which is the private key, and then use it to crack the message. Let's look at the code. So here's the code we're going to use to find prime numbers and then determine if a number can be prime factorized. At the top, is some description for this code. The following statistics are generated by CPU i3-8100, which is my dad's computer. So on my dad's computer, it takes, for numbers that are less than or equal to 100k, it takes 0.2922 seconds to find all the prime numbers. And the greatest prime number is 99,991, and it has 9,679 prime numbers in total. If we're testing all the numbers that are less than or equal to 1 million, then it takes 6.6419 seconds, and the greatest prime number is 999,983, with 78,703 prime numbers in total. So next is the code part. In the first line, we import time because we're going to use it to see how long we take to find prime numbers and stuff. So we need to import this. In the second line, we create an empty list called num. This is the list where we're going to put all of the prime numbers that we find. And then the next two lines are the range for the prime numbers. So we want to start from I, which is 2, and all the way to k, which right now is 100,000, because 2 is the smallest prime number and 100,000 is the limit that we want to go. So we're gonna find prime numbers between 2 and 100,000. So the maximum for k for our code is 1 million, which is 7 digits. If you don't want to wait for a long time, just use 6 digits for k, which is 100,000, because we know that when it's 1 million, it takes 6.6419 seconds to find all prime numbers. So right now, we're going to use 100,000. And then we find the timestamp for when we start. So start equals time.time brackets. This finds the current timestamp. The current timestamp is the number of seconds since the year 1970. So whenever we run the code, it has a different timestamp, and we can use that timestamp to make calculations to see how long the code has been running for. The next line is a different variable. Now it equals time.time. So these two variables will be very similar. And then we have a while loop. So as long as now minus start is less than 60 and I is less than k, this while loop continues. So these two are the two conditions that the code has to meet in order to do this. So if we do now minus start is less than 60, which means that if the code has been running for more than 60 seconds, we want it to stop by itself. Because now minus start, every time this while loop finishes, it finds a new value for now, and then we test it to see if it has been 60 seconds yet. And the other condition is I has to be less than k, because every time the I gets added 1 as well. We want to test the numbers all the way to k. So as soon as I equals k, this loop stops. So while this loop is running, it will have to be less than 60 seconds and it will be a number under k. So inside the loop, we're going to test to see if the number is a prime number. So we have this variable j equals 2, and then we have this line, loop is the integer of I to the power of 0.5. This is the loop amount. For example, we use integers from 2 to square root 11 to see if 11 is a prime number. Let me explain this line a bit more clearly. So if we want to see if 11 is a prime number, we just need to divide 11 by integers between 2 and root 11, because we don't need to try any of the integers between square root of 11 and 11, because if there is a factor of 11 in range 2, then there has to be a factor of 11 in range 1. So let's say there is a factor of 11 in range 2 called x, and then x times y equals 11. If this x exists, then this y would exist. So by checking all of the integers between 2 and square root of 11, we will find all of the possibilities of factors of 11. So if we don't find any factors of 11 between 2 and square root 11, then there mustn't be any factors of 11 between square root 11 and 11. That's why we only need to try integers between 2 and square root 11. So this line tells us how many loops we need to try. And then here we are going to try the integers to see if the number is a prime number. For j in range 2 to loop, starting from 2 all the way to loop, we see if I divided by j has a remainder of 0. So first I starts from 2, so we see if 2 divided by j has a remainder of 0. If it does, then this loop breaks. That means we have found a number that is not a prime number, because whenever something has a remainder of 0, that means it can be divided, which means it's a factor of the number. So we don't want that number anymore because we're looking for prime numbers. But if it isn't a prime number, this doesn't break. And then we will run this else part, in which we will add the I into the num list. So when we see if a number is a prime number, if it is, we add it into the num list. If it isn't, we break and then try the next number. And then this happens all the way until we reach I is equal to k. So we will try all integers from 2 to 100,000, unless it passes the time limit, which is 60 seconds, but it probably won't happen. So after this finishes, we find the current time again, and then we print the amount of time used for the loop. So we print the string time used for loop, and then now minus start, which is the amount, and then seconds. So let's run it. So the first print printed this. So we used 0.32 seconds to find all prime numbers between 2 and 100,000. Next, we print the prime numbers in list and num, which is the list of all the prime numbers. So that's in this squeeze text here. This contains all of the prime numbers that we have found. But there is a lot, and it causes this to be laggy, so I'm going to run it again. So you guys can see that there are a lot of prime numbers in a list. Okay, let's continue. After we print all of the prime numbers in the list, we make 2 copies of the list, because we're going to change the list, so making some copies makes sure that it doesn't get lost. So we make a copy called A and a copy called B. And then we reverse the list. So list on num.reverse turns the order of the elements in the list, like it flips it. So the first element becomes the last element, and the last element becomes the first element. And doing this does not return a value, it just changes the list. After we do that, we print the list length and then the length of num, which is the list. So right now, the list length is 9,679. That means we have found 9,679 prime numbers. And then we print the 10 biggest prime numbers in the list. And this end equals empty string just tells it to not skip a line. Here we're going to print the numbers, which are these. So we want the first 10, so the range is from 0 to 10. We print the numbers in the list starting from 0 all the way to 10. And then each time we print a number, print a space and not skip a line. So the first time it prints 99991, and then the second time it prints 999989, all the way to the 10th number, which is 99877. These 10 numbers are the biggest prime numbers that we have found. And then we print an empty line, which tells it to skip a line, because at the end we have this don't skip a line, but we want it to skip a line because we're doing something new now. And then we print verify list length and then length of A, which is a copy of the list. So the copy of the list is 9,679, which means that these two lists are still the same. And then we verify it again with B, which is also 9,679. After that, we find the binary of 1 million times 1 million and print that. So that's this number over here. That's the binary of 1 million times 1 million. And then we turn that number into a string and give that string to character bin. And then we print max binary length that can be prime factorized by current algorithm in limited time frame, and then the length of character bin -2. We need to -2 because in this number, the first 2 digits are just saying that this is a binary number, so we don't actually, that's not part of the number. So this is the number, so we need to -2 to find the actual length of the number. So that we printed this line. Max binary length that can be prime factorized by current algorithm in limited time frame is 40. And then we print the line, it's only 40 bits long, far from 1024 bits. So our code can only prime factorize numbers that are 40 bits long, but in real life, numbers that are 1024 bits long can all be prime factorized. So now we have finished finding all of the prime numbers. We can go on to prime factorization. Here is the function that we're going to use for prime factorization. So the function's name is called prime factorization, and it takes in the number big N. So it's going to take big N and see if it can be prime factorized. If you don't want to wait a long time, make big N less than 10 digits, which is in decimal form, not binary form. So if you make big N less than 10 digits, it should be able to prime factorize it within a reasonable amount of time. In the function, we find the timestamp begin equals time.time, and then we try different numbers, different prime numbers, to see if their product is the number. So this is the logic that we're going to use to see if a number can be prime factorized. We try multiplying all of the possibilities of 2 prime numbers together. So we start with 2 times 2, and then we see if that number is big N. And then if it's not, we try 2 times 3, 2 times 5, 2 times 7, all the way to 2 times 99,991. If all of those numbers, like the product of these numbers, are not the big N, then we go on to 3 times 2, 3 times 3, all the way to 3 times 99,991. So that's what we're doing in this code over here. We have two for loops. In the first one, we have for m in range length a, and then in it we have for n in range length b. So for the first time, it's going to be m equals 1, n equals 1, and then in here, for the first one, m equals 0, n equals 0, and then in here we're going to see if big N equals the 0th element in list A times the 0th element in list B. So basically, if 2 times 2 equals big N, because the 0th element in A is 2, and the 0th element in B is also 2. So if 2 times 2 equals big N, then we print big N can be prime factorized. The factors are 2 times 2, and then we return 2 and 2. So that if this happens, then the function stops, and then we have found the two prime numbers that have a product of the number big N. But if the 2 times 2 does not equal big N, then it goes on to the next loop. So the next one, N turns into 1. So we're going to try if the 0th element in list A times the first element in list B equals big N. So if 2 times 3 equals big N. If it isn't, then nothing happens. But if it is, then we print this and return 2 and 3. So this process continues. If two numbers have been returned, the function ends. But if it isn't, then this loop just continues all the way until we get 99,991 times 99,991. If all of those numbers have been tried and none of their products equal big N, then we will go on to this part of the function. We find the current timestamp again and then print prime factorization used this amount of seconds, but big N cannot be prime factorized. And then we return 0 and 0 to mean that no numbers have been found. So this is the function that we're going to use to prime factorize a number. And then here we're going to run the function. We're going to run the function with 99,991 times 99,989. We know that this number can definitely be prime factorized because it is the product of these two prime numbers. So when we ran the code, we found this. So this number can be factorized, prime factorized, and the factors are 99,989 times 99,991. So our code was successful when these two numbers, their product, can be prime factorized. Now let's try a number that cannot be prime factorized, such as 99,991. It can't be prime factorized because we know that this itself is a prime number. So the only factors it has is 1 and itself. So when we run the function on this number, it says prime factorization used 10.84 seconds, but 99,991 cannot be prime factorized. So our code has been successful. Lastly, there is some additional information. So there is a thing called fundamental theorem of arithmetic, which is also called the unique factorization theorem and prime factorization theorem. This theorem states that every integer greater than 1 can be represented uniquely as a product of prime numbers up to the order of the factors. So this means that the result of each prime factorization is unique, and if the number is an integer greater than 1, then it can always be prime factorized. the fundamental theorem of arithmetic says that every integer greater than 1, you can prime factorize it, and there is only one answer. So for example, if you do 2, then it can be prime factorized into 1 times 2. Also, 1 times 2 is the same thing as 2 times 1 because the factors are ordered. So also, it can be the product of more than one prime number. For example, 8 can be prime factorized into 2 times 2 times 2, and so can any other number greater than 1 that is an integer. And lastly, we have some statistics from trying this code. Prime factorizing 93,683,041, which is 9,679 times 9,679, takes less than 15 seconds. But if we prime factorize 999,983 times 999,971 will take 892 seconds, which is 14 minutes. So that takes a much longer time. Currently, this code can prime factorize up to 10 to the power of 7 times 10 to the power of 7, which is 1 million, which is 14 digits. That's the limit of this code. In the future, dichotomy can be used to find the result more quickly. Dichotomy is basically, instead of trying all of the prime numbers, we can try 2 prime numbers. If their product is too small, we can find a number between this number that was too small and the biggest number and try that one. If that one is too big, then we find a number that is the previous number and this number a number that is in the middle of the previous number and this number. So if we do it like that, the code would be more complicated, but it would be faster and more efficient. That's the end of my presentation. Thank you.